I have you loud and clear.
Hello.
Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
Space.
Time.
the brain,
Life.
The universe.
This week we are diving into the first episode of a month of marine science with a trip to the seaside. We'll be investigating the science behind sand, how an invader from the Gulf of Mexico has turned up in England, and the sponge that is saving our coastlines from oil spills. Plus, how scientists have created the brightest light on Earth, new news on fake news, and a drumming bird nicknamed, you've guessed it, Ringo. I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
First this week, a new technique to see inside tissues in 3 dimensions so doctors can make better and much faster diagnoses, including even during an operation, has been invented by scientists in the US. In the new system, a flat sheet of light is used to illuminate a series of very thin slices through a block of tissue. The light that emerges is captured by a camera, which builds a 3-dimensional picture of the entire specimen. The University of Washington's Jonathan Liu helped to invent the technique.
The way to think of it would be as a flatbed scanner for tissues. The sample sits on top of a glass plate. All of the optics are underneath, so the light and all of the complexity is hidden underneath that glass plate. All the user has to do is place the tissue on top.
And what sort of tissue specimens? How big? What can you image?
So that's something that's rather unique about our system in that it's somewhat unconstrained in terms of the types of specimens that you can place on top. We've imaged tissues as large as 5 by 5 centimeters. These are relatively large surgical excisions. We can also image smaller specimens, 1 millimeter in diameter, core needle biopsies that are obtained from patients who are suspected to have tumors.
So if you had a person undergoing surgery, the key question a surgeon wants to be sure of when they're operating is, have I removed all of this person's cancer, for example? You could take the tissue that's come out of the patient and you could image the block and see if there are what we call clear margins. There's an area around the tissue where there are no cancerous deposits, so the surgeon knows that they haven't got to return that person to the theatre later for another operation.
That's correct. And there are alternative technologies that have been attempted, for example, frozen sectioning, where they freeze the tissue so that they can cut the tissue very rapidly during surgery. But these techniques generally do not produce very reliable results. And for certain tissue types, for example, fatty breast tissues, they don't work well because fat does not freeze well. So it's very difficult to obtain a high quality image.
So tell us then how it actually works. So you get some fresh tissue hot out of the patient. It goes on your glass surface. What's going on under the hood, if you like, to make this possible?
Traditionally, with pathology, the tissue has to be chemically processed, mounted in a wax block, sliced into very thin sections that are mounted on a glass slide, and looked at under a traditional microscope. With our technology, we don't have to cut the tissue. We use light to slice into the tissue. This is something we call optical sectioning as opposed to physical sectioning with a knife. So we send in a thin sheet of light and we image that sheet with a camera so that we can see an image that looks like the tissue has been sliced into a very thin section without having to actually cut into the tissue.
I've got my block of tissue sitting on top of the microscope. The light's coming in from below. What, does it come in at an angle to create that light sheet? And then how does the camera see what the light sheet is seeing?
Right, that's correct. In order to image the light sheet, our camera has to be situated at a 90-degree angle to that light sheet as it enters the tissue. So instead of sending in the light perpendicular to the surface of the tissue, we send it in at a 45-degree angle. And then the output beam also exits the tissue surface at a 45-degree angle. As a result, we can image these oblique light sheets that are cutting into the tissue at 45 degrees. As we scan the tissue, we collect a series of these oblique light sheets so that we can obtain a 3-dimensional volume of the tissue.
And can your computer recompile each of your sheets on slices through the tissue to produce a 3D model effectively on the screen of what the microscope is seeing?
Yes, exactly. That's the intent of the device, is to collect these 2D light sheets and to reconstruct them into a 3D volume so that we can display to the pathologists and other clinicians the 3D microarchitecture of the tissue, which should allow them to understand the tissue, to understand the disease, and to guide patient treatments ultimately more accurately. And so we feel, and we've shown in the paper, that there are much more accurate diagnoses that can be made based on the 3D information.
And if this lives up to your expectations, what sort of a difference will it make for the patient?
For treatment, this can make a huge difference. There is a problem that's recognized now, especially for prostate cancer patients, as well as breast cancer patients. A lot of these patients are being overtreated, where they'll receive surgery or chemotherapy or radiation therapy when it's not needed. And these therapies all have side effects. So it's very important that we can stratify the patients to determine which patients should be treated and which patients maybe should just undergo active surveillance, and perhaps the disease won't actually be very malignant. In prostate cancer, most of the cancers are not very aggressive, but for a small fraction of patients, they can lead to death, and we need to be able to identify those patients for the appropriate treatments.
It's amazing stuff, isn't it? That's Jonathan Liu, and he published that work this week in the journal Nature Biomedical Engineering. Now, staying with the very small, when light particles, called photons, hit the electrons in the atoms that things are made of, the light is scattered back, and this is the very reason that things are actually visible in the first place. But now scientists at the University of Nebraska-Lincoln have created the brightest light on Earth. And they found that these sorts of energies, when substances are illuminated, something very exciting happens that could make a massive contribution to both healthcare and security. Izzy Clark spoke to Donald Umstrada about the light source he's made and what happens when it illuminates something.
It's about 1 billion times brighter than the surface of the sun. In terms of power, it's got the power of all the Earth's electrical grid, but it's only on for a very short time. To make high brightness, you need to have that power of light focused to a very small spot. We focused it to an area that is only about 1/1,000,000th of a meter in diameter. We're producing the most photons per unit area that has ever been produced on Earth.
Donald and his team amplified short pulses of light up to high energy in a laser system. That makes this light of a high power, which is equivalent to 1 trillion light bulbs. But that only occurred for a very short amount of time. By concentrating that power into a tiny spot makes the light incredibly bright with high intensity. Next step was to aim this extremely bright light at a minute target, an electron. But how?
Well, what we're using is a mirror that has a curved surface, so we call it a parabolic reflector that allows the rays to be focused at some distance away.
These parabolic mirrors are similar to those used in radio telescopes. Looking at how light interacts with matter is a fundamental part of physics. Under typical conditions, when the light from a bulb or the sun strikes a surface, it's scattered by an electron, and this is what makes vision possible. With light of a standard brightness, the electron will scatter the photon at the same angle and energy it had before striking the electron, regardless of how bright that light might be. Yet, Donald's team found that, above a certain threshold, the laser's brightness altered the properties of the scattered light.
Well, the electron responded to this brighter light by emitting a new light that had much more energy than the original light. The energy was high enough that we would call it an X-ray.
That phenomenon stemmed partly from a change in the electron's movement, which abandoned its usual up and down motion in favour of a figure-8 pattern. It was found that the ejected photon had absorbed the collective incoming photon energy, granting it the energy and wavelength of an X-ray. Whilst this theory had existed for decades, this behaviour in light had never been documented. Let's break this down a bit more. Imagine you had a dimmer switch in your kitchen. At low brightness, your table would appear dark, but as you turn up the switch, it gets brighter and more visible. This is what happens when we use standard light to see. But hypothetically, if your dimmer switch was controlling this ultra-bright light, it's as though your table would have suddenly disappeared. The light waves that are being scattered back from the table have turned into X-rays, which we cannot see. But an X-ray scanner can, of course.
The typical X-ray you get at a hospital is more like a light bulb than it is a laser, and so produces all frequencies of X-rays, and it produces them over all different angles. And most of those X-rays are wasted. X-rays can also give you cancer, and so the dosage has to be kept below a certain level. It turns out that the X-rays we produce good quality images with 10 times lower dose, and so they're much safer and better quality.
X-rays are also used within security. Is there the possibility that we could use X-rays to improve security as well?
We have shown that the X-rays we are producing this way can penetrate through very thick steel and still get a very good image of what is hidden behind that steel. There's a big concern that nuclear materials could be transported through cargo containers, and so it's very important to be able to inspect cargo containers for such threats in a rapid and non-destructive way, and that's what we've demonstrated with our X-ray source.
Illuminating stuff. That was Donald Umstrater, and he was talking with Izzy Clark about the work he's just published in Nature Photonics. You're listening to The Naked Scientists with me, Chris Smith. Still to come, why fake news is so prolific and the residents from the Gulf of Mexico that are invading Europe. But first, it's time for this week's Down to Earth, where we take a look at the tech intended for space, which has since found a new home down here on Earth. And this week, physicist Stuart Higgins is hoping you're sitting or laying comfortably.
What happens when the science and technology of space comes down to Earth? Hi, I'm Dr. Stuart Higgins, and welcome to Down to Earth from The Naked Scientists, a mini-series all about the space tech that's being used back down on Earth. This episode, we're talking about the granddaddy of space spin-offs, a story with such a relaxing ending, it might just send you to sleep. Yes, we're talking about memory foam. Back in the 1960s, NASA wanted to improve the survival rates of aircraft passengers during crashes. Even if the aircraft fuselage doesn't break up during a crash, the sudden deceleration can still cause severe injuries. Aeronautical engineer Charles Yost came up with a solution. In 1962, he'd been part of the team that developed the parachute system for the Apollo command module for its return to Earth. But his solution for improving crash safety was something altogether more squishy. He developed a special plastic foam that could be used in seat cushions to absorb the energy of an impact, helping to protect passengers. You can think of plastics as being made up of lots of interlocking chains, a bit like a tangled plate of spaghetti. The overall properties of the material depend in part on just how tangled up those chains are. Yost trapped a gas inside the plastic as it was being formed, turning it into a bubble-filled structure and fundamentally altering its material properties. What was really interesting about the foam he created is that it was viscoelastic, meaning that it behaves a bit like a thick viscous material, like honey, but over time also bounces back elastically to its original shape. This technology went on to become the basis for the memory foam mattress. These are made from polyurethane, which surprisingly is the same plastic used in skateboards' wheels. But with the right processing, what is a hard, durable plastic can become a springy foam that temporarily holds the shape of objects pressed into it. So presumably NASA astronauts have some of the comfiest memory foam mattresses in the solar system, right? Well, not exactly. In fact, memory foam mattresses never made it to space. You don't need a mattress when you're sleeping in zero-G, just a sleeping bag. And although the foam was initially developed by Yost and NASA, the mattresses came much later. Although coincidentally, nowadays NASA makes astronauts who've just returned to Earth walk around on a memory foam surface. They use it to test how well the astronauts can balance to see how they're coping with gravity again. You might say that the memory foam surface is helping astronauts by putting the spring back in their step. That was Down to Earth from The Naked Scientists, and join me again soon to learn about more space technology that's changing lives back on Earth.
Thank you, Stuart. And next time, Stuart's going to be explaining how the Indian space programme is throwing a lifeline to fishermen. Now, we've heard a lot lately about fake news, which is going up the agenda with claims that it's misleading the public and it could even be compromising elections. And despite many people being aware of the problem, it's not going away. So why is it so prolific? Filippo Mensa from Indiana University has made it his mission to find out. And Tom Crawford heard how.
So here what we wanted to look at was, even if we assumed people can do a good job recognizing high-quality information from low-quality information, and further that they prefer to select and share high-quality information, how does then this play in the broader dynamics of social media? In other words, is good quality information likely to go viral more than junk and fake news? And so we built a model to study that particular question.
What did you find out then? Was the high-quality information more likely to go viral?
Well, the short answer shortly is no. So we looked at two particular factors in our model. One is how much information is produced, which determines the information load that people experience. So if a lot of information, if a lot of things are posted, then people get a lot of stuff in their feeds and they can't possibly, pay attention to all of it. And on the other side, on the consumption side, we modeled how many things people are capable of paying attention to. We have finite attention, and all of this information is competing for our limited attention. When we make realistic assumptions about these quantities, these limits, then what the model shows is that low-quality information is just as likely to go viral as high-quality information. Statistically, we cannot distinguish between the popularity signatures of low and high quality information.
And what about things such as bots? So I remember reading something, I think it was Katy Perry had reached 100 million followers on Twitter, but then actually reading the article in detail, it was saying that up to half of these are believed to just be fake accounts or bots. Are they also playing a role in spreading fake news?
Yes, people who are running fake news websites are also using bots to amplify the visibility of their posts, whether to monetize it and make a financial gain through ads or simply to manipulate public opinion. Creating bots, even pretty sophisticated ones that are hard to tell from real humans, is relatively simple. And we have found that they are extremely effective at pushing fake news to go viral. So they create the impression that many people are paying attention to it, which makes people curious to see what it's about. And so this then creates a loop by which they are able to generate a sort of a cascade.
How can we then try and stop this? Or how can we tell if some account is a bot?
It is a hard task, and it is getting harder because bots are becoming more sophisticated. We've been working on machine learning algorithms to detect social bots for a few years now, and in the early stages, bots were pretty simple. They just automatically tweeted or retweeted, and you could see their patterns, and you could recognize them from, long names and numbers and so on. But now we find much more sophisticated bots that are driven by humans. Very often the content itself is generated by a human, but instead of being posted on one account, it is posted on 1,000 or 10,000 accounts. And then these accounts follow each other and follow other people and respond and reply to humans so that they create networks that make it quite difficult to detect them.
So don't believe everything that you see on Twitter, unless it's from @NakedScientists, of course. That was Filippo Mensa, and his work was published in Nature Human Behaviour. Now, from bots to beats. Birdsong may sound beautiful, but does it really count as music? And can birds keep time? Georgia Mills has been sounding them out.
Some kind of music exists in every culture in the world. But does it stop with humans, or do our friends in the animal kingdom enjoy a beat or two? Elizabeth Tolbert is a professor of ethnomusicology at Johns Hopkins University and is interested in this very question. I caught up with her to find out if we knew when music first began in our own species.
So if we are talking about music as we understand it today, it's a human cultural form. So basically the question would then be, when did human culture begin? And that's a thorny question, but if you look at the archaeological evidence, we don't really see much manifestation of symbolic thought until after the evolution of anatomically modern Homo sapiens. So there may have been a lot of precursors to music-like behaviors, but actual music in terms of being a cultural form came with anatomically modern humans.
Do we know why music started? Why it's this important thing to us?
That's also a hotly contested topic. So my particular take on it is that music is part of the broader spectrum of human symbolic communication, and that it's kind of on one end of a continuum. It's on the end of the continuum which is about sociality and relationality. The other end might be language, which is about referring to specific objects in the environment. But both of them have to do with the imaginary worlds that humans create to interact with one another. So I would say that whatever drove us to have a certain kind of sociality, the offshoot of that was that we were able to create these imagined worlds, and we need both the glue to keep us together so that we believe in these imagined worlds, and we need more specific things that point us to actual events and things, language, music.
And are humans alone in this ability to make music? Because when I think of music, I also think of things like birdsong, I suppose. So is it just humans who can do this?
Again, hotly contested and debated topic. From my perspective, music is a human activity because it's part of culture, and I also consider culture to be a human activity. So there are a lot of sounds that animals make that sound like music to us. Included in this are things like, bird song is the obvious one, but whale song, absolutely beautiful. But we are the ones that are making them musical, not the animals. So when we sample some bird sounds, the composer might sample some bird sounds and put them in a composition, it's framed as though that's some kind of musical being that is uttering that. That's what we attribute it to. And I think that the way we attribute subjectivity and intention to sounds is what makes it music, not the sounds themselves.
We could argue then that it's our specific human interpretation of something which makes it musical. Birdsong might sound lovely to us, but we have no evidence to suggest birds even hear it in the same way we do. And even something relatively simple like tapping a beat, most animals seem to struggle with one notable exception.
I'm Christina Zdenek, and I'm currently a PhD candidate at the University of Queensland. Picture a quiet remote area in the far north Queensland of Australia.
This is the home of the palm cockatoo. Christina's been tracking them over 7 years to document an extremely rare behaviour, all the while living in some very luxury conditions.
For a couple of years, there was this humpy, which is like a shelter shed with only 2 walls and a ceiling and a floor. And so, the butterflies and bats fly through the place and the snakes just slither through the rafters, and you sort of only have like a third of the place that stays out of the rain.
So what is this behaviour that was worth spending months on end living in a glorified shack?
So I was after drumming behaviour.
Can you hear it? That tapping is made by a cockatoo. It's wrapping a drumstick that it's made from a twig onto a tree trunk. This is the only known example of an animal actually making a tool to make sound. And they're pretty good at it.
There was one bird in particular. He had a bit of a ring on his bill, and that was really distinctive. And because he had the ring and because he was drumming a lot, I called him Ringo. And he would drum for ages, like compared to other birds. Like there was one of his sequences that went for over 14 minutes, and it was consistent. He kept a rhythm, and it was the same rhythm throughout.
Move over, Ringo. But why are these birds drumming in the first place?
Leading up to breeding is when these birds are drumming, and the majority of the contexts in which I recorded them drumming is where the male is doing it with an audience of one, and that audience would be a female, and that was his mate. So we don't think that it's to attract the mate, but more so for pair bonding, and this could be really important for them in sort of gearing up for breeding.
All this effort simply to impress their mates. And this does give us an insight into our own species. Perhaps early humans started drumming in the first place for the very same reason.
That was Georgia Mills. She was speaking to Christina Zdenek at the University of Queensland, and before her, Elizabeth Talbot from Johns Hopkins. And the paper on palm cockatoos and their drumming habits is out this week in Science Advances. You're listening to The Naked Scientists with me, Chris Smith. And over the next 4 programmes or so, we're going to be dipping our toes into all things aquatic because we're calling July Marine Month. And across the series, we'll work our way down to the bottom of the deepest ocean on Earth and find out what's in there. Also with me is Danny Green. She's a marine ecologist from Anglia Ruskin University. A very warm welcome to her. And Danny, I suppose it's fair to say that most people regard Earth's oceans as both massive but also massively underappreciated and under-researched. Would you go along with that?
Yeah, I mean, there's a lot that we don't understand about processes and biodiversity in the oceans, but they are extremely important. I mean, you know, they're over 70% the surface of the Earth. They help regulate the climate. Extremely important links to global climate change and carbon cycling in the ocean.
What are the biggest threats facing the ocean, in your view?
Overfishing is a huge one. Habitat destruction, pollution that's physical and also chemical pollution. Quite a list, actually.
And what about the good news stories, things that you think should be championed about the seas?
People are really interested in the oceans, and I think that's great. And there's a lot of really good citizen science projects getting people to report back when they've seen invasive species, to counting plastics and microplastics and things like that. I think people really want to improve the quality of the oceans.
Place to have a lot of fun too, isn't it? Danny's with me throughout the programme. We'll come back to her in a second. But the reason I brought up the idea of fun is that we're actually going to launch our tour of the marine realm at the beach, predictably enough. I have in front of me something that beaches are probably best known for, and that is, of course, sand. I also have a granular materials scientist. He's not granular. What he studies is. That's Matt Aaron. He's from the University of Cambridge. And he also knows a thing or two, I'm told, about building a supreme sandcastle. Matt, when we say sand, what actually is sand?
So most sand is lots of rocks that have been ground down over millions of years in the oceans or in the rivers. It can be corals that are ground down on some tropical beaches, or in the case of Iceland or some bits of Scotland, it can be volcanoes that have been ground down to make black sand.
And that's why the sand differs in colour and texture and composition.
Yes, exactly. And that turns out to be important for sandcastles too.
Speaking of which, what have you got in front of you?
So in front of me, I have a metal tray, a big one like you'd use for doing a roast. And in the tray, I have 3 plastic cylinders. So they're about 20 centimetres high. And in each cylinder, I have some sand, as you'd expect. In one tube, it's dry. In another tube, I have it completely saturated with water, just as you'd find at the beach. And in the third tube, I have it half saturated with water. So the key is to show what amount of water do you want to add to build the best sandcastle.
OK, so we've got this tube. It's an open top and bottom cylinder, 3/4 full of sand, and you're going to lift it up. Well, the sand in there is dry, and I would speculate that in the same way as I turn my salt cellar over and salt comes out, I suspect the sand's just going to go everywhere.
Exactly. So if I pull it up,
yep,
the sand,
we now have a tray.
Pull it at the bottom. So dry sand doesn't work for a sandcastle.
OK, I didn't need to have a PhD to know that one. I think that was relatively easy. So which one are we going to do next?
Now, wet sand should work. So I'm going to just top up this final cylinder so it has lots of water in. It has as much water as the sand can hold. And I just pull up the tube. And we see it slumps out the bottom.
It did come out in sort of sausage shape, but then it quite quickly just, as you say, slumped, and it has flowed, almost like it was a liquid, over the bottom of the tray. And we now have a very poor representation of a sandcastle from that one.
It's not very impressive, is it? No. It's not what you'd do if you wanted to...
So is this the Goldilocks, the just right one?
Yeah, so if you have a mix of about 1/4 as much water as you have sand, and you fill a tube with it, I'm just going to tap this down, stop it coming up with the tube.
So the magic ratio is 1/4 as much water as sand?
So it depends on what you're trying to achieve with your sandcastle, but a good bet is about 1/4. So if I pull up...
And you're just drawing the tube upwards. It's holding. It's looking pretty good. So what we've basically got is a sandcastle. It's about the shape and size of a big beer can.
Yeah,
and it's holding.
Exactly.
It's standing there. Right, so granular materials scientist that you are, why does that work and yet the one that had lots more water, clearly water is important because it's helping this one to stand up so beautifully. Why was too much water bad and no water terrible?
So the key to this is surface tension. So this is the same sort of force that keeps the droplets on your tap from falling down immediately. And sand is interesting because about half of it is just empty space. So when you add water to sand, that water can fill in that empty space. With a dry sand, you have no water, so you have no forces bringing these grains of sand together, and so it just flows out. When the sand is full of water, all of the water is there, so you have no surface tension because there's no air, there's no gaps. The water can just flow along with the sand, and it flows out. But when you have a mix of about a quarter as much water as you have sand, then the water forms bridges between the grains, and the surface tension brings the sand grains together, sticking the sand together and making it cohesive.
And it's fabulous to now know how I can make such an amazing sandcastle map. But the thing is, I don't want people to go away thinking that you do nothing but gratuitous sandcastle research, because actually this is really important. There is an important science side to this as well, isn't there?
This sort of cohesion and the strength constrained by water is very relevant to coastal erosion or landslips. We need to know how wet a soil needs to be before it collapses and flows, which can damage homes and people's livelihoods.
Now, obviously, you don't go building sandcastles in the laboratory very often, or do you? Is there not, say, a computer model that you could build for these sorts of interactions in order to work out how much sand to add to your cement and how runny it's going to be, or how likely the hillside is likely to collapse if we have a heavy rainfall, for example?
So, famously, there are an awful lot of grains of sand on a beach. And so it's very hard to build a computer model that includes all of them, or even any significant number. In this tube, there's going to be about 1 million, at least, grains of sand. And you can't build a computer model that takes all of the physics into account of every one of them. So sometimes we have to do actual experiments just to work out the basic physics that are going on.
It's good old-fashioned legwork and spade work. Matthew, thank you very much. Well, that's the science of actually granular materials, Danny, but what about the biology of these sands and sediments? That's pretty important too, surely.
It's really important, actually, and it's been estimated that in just less than 1 gram of sand, there's over 2,000 different species of microbes, which isn't really surprising if you think about it. It's probably even more in mud. But these microbes actually excrete extracellular polymeric substances, and these help to cement, to sort of glue together the sand grains, which is really important for stabilising sediments. And this is why they've tried to stop people from driving four-wheel drives over sandy beaches, because it breaks this bond and means it can lead to more erosion as well.
And the sea doesn't do that itself when the tide comes in?
It does as well, but further up on the shore, where you only get the tide reaching at really high tides, it's quite important to have stabilised sediments.
Thank you, Danny. Well, now we're going to dig a little bit deeper in that sand, and we're going to hear about a group of creatures that live in sand and why these creatures are extraordinary timekeepers, because incredibly, they can predict the times of tides. David Wilcoxon studies this at the University of Aberystwyth. So, David, before you tell us about the timekeeping, what actually are these creatures?
These creatures are a relative of the woodlouse, which most people are fairly familiar with, I'd imagine. And they've got a scientific name, which is Eurydice pulchra, after the Greek mythology Orpheus and Eurydice. And we know them as the speckled sea louse.
And what do they do? What's their sort of life cycle?
So, I mean, they're a beautiful animal, and they're a fascinating animal because they live buried in the sand. That's about 10 centimetres, usually less. And they emerge from the sand when the tide comes in, and they swim around, they feed, they mate. But critically, they burrow back into the sand before the tide then retreats as the tide goes out. And the reason for this is because they want to maintain their preferred position on the shore. They don't want to get washed out to sea. They also don't want to get washed too far up the shore. So using this timing mechanism, which is based on a tide or a 12.4-hour cycle, they can maintain their position or their station on the shore.
Because, of course, there are high tides every 12 hours, aren't there? So how do they do that? How are they keeping time on a 12-hour basis? Because obviously we're familiar, you and me, with, and pretty much every living thing on Earth has a body clock and can keep time, but most body clocks we see keep 24-hour time, not 12-hour time.
And that's the sort of the crux of a long-standing argument in biologists about the nature of timekeepers. So you're quite right. We have a circadian or a 24-hour clock, as do nearly all terrestrial organisms. And marine biologists have been arguing about whether animals actually have a bona fide or a dedicated 12.4-hour clock, or whether it's just some sort of modification of this 24-hour clock. we have fairly recently discovered that whilst the speckled sea louse has a 12.4-hour clock, it does have a daily or a circadian clock as well. But we can actually separate them or disentangle the two clocks to show that they are separate entities. So they have a dedicated 12.4-hour clock and a daily clock that operate slightly different behaviours.
Is it working in their brain or nervous system in the same way that I have in my nervous system a cluster of nerve cells which have a sort of genetic clock ticking, keeping time like a genetic domino effect, so it ticks around taking 24 hours to do it? Do they have the same thing for 12 hours?
We believe so. We're still working very hard to fully identify the cells in the brain that operate this, but we're pretty sure we have a good idea that this is occurring in the brain alongside the 24-hour clock, yes.
And the 24-hour clock, is that set by daylight in the same way that mine is? Because I get up in the morning, nice deluge of bright blue light strongly activates my body clock and says it's morning. Do these creatures have a light-sensitive clock too?
Yes, it is light-sensitive, Chris, and this has been important in our sort of dissection of the 24-hour and the 12.4-hour clock in this animal. We can actually take Eurydice, or the speckled sea louse, off of the shore, and we can put them into altered light regimes, and we can change aspects of their 24-hour clock. They have these beautiful cells, these chromatophores, these colour pigment cells all over the back of the animal, and they contract and expand on a 24-hour basis. And what we can do is we can manipulate that using different light regimes. And the other thing we can do, and what a lot of chrono or clock biologists use, is constant light to disrupt rhythms. Organisms don't like to be in constant light. It messes with their biological clock.
So that would include like artificial light. If you deluge the shoreline in artificial light, this could also disrupt this clock.
Absolutely. And what we did actually is we took animals from the shore, we put them into constant light, and we found that these pigment cells, the rhythm of those was demolished. It was completely messed up. But the tidal rhythms, this 12.4-hour swimming, was left intact. And that's one of the clues that told us that there are two systems operating independently.
I'd just like to bring Danny in here because obviously these are small crustaceans, Danny, but there are many other bigger creatures that could also be disrupted in the oceans then by artificial light from humans.
Yeah, exactly. So if you think about the fact that the majority of cities in the world are situated by the coast, there's a lot of artificial light along shorelines. And there was a study recently by Bolton et al. In Science of the Total Environment 2017, and they found that artificial light actually made predators more active. And this had cascading effects on the communities of invertebrates that were in the area because they just didn't stop eating. They wouldn't stop because it's like if, that's why they shouldn't put a light in a fridge, I reckon, at night to help me with my diet. But so basically they just eat all the time. And this had, huge effects on the communities.
Thank you, Danny. And thank you also to David Wilcoxon, who told us about his work he's doing at the University of Aberystwyth. This is The Naked Scientists. I'm Chris Smith. And it's Marine Month. Still to come, the sponge that could save our shorelines. Now, while we've looked at the species that should live on the beach, what about the ones that shouldn't? Increasingly, what are called invasive species are turning up in many countries. These are animals and plants that are not naturally found in a particular area, but they've been introduced there, and because there are no natural predators and very little to compete with them, their population explodes and they drive out the native species. In the last year or two, scientists have discovered a species of clam that normally lives in the Gulf of Mexico, on the other side of the Atlantic Ocean, thriving in some waterways in Lincolnshire, on the UK's east coast. Izzy Clark joined the field team who are studying its impact.
You might not associate grassy banks with the coast, but estuaries can take many forms. It's in this transitional zone where a river meets the sea and provides vital nesting and feeding habitats for many aquatic plants and organisms. I joined David Aldridge and his team from the University of Cambridge as they waded through the South 40-foot Drain, an estuary in the Lincolnshire Fens, all in search for the rather mysterious Gulf wedge clam.
Today we're trying to understand some pretty fundamental stuff about an organism we know next to nothing about. The Gulf wedge clam was discovered in the drain here in 2015, but unusually we have very little information about the impacts of this organism.
Generally, how do coastal invasive species go from one place to another?
Certainly globally, in brackish water systems like this, one of the major pathways is through ballast water of ships. That's where water is picked up into the bottom of a ship to stabilise its weight when it goes across the ocean. It goes to a new port, and takes on its cargo, and then releases that ballast water because it's now balanced by the weight of the cargo. But therefore you get organisms transported from a brackish water or freshwater system across the ocean in the hull of a ship, and then down into a new freshwater location, and you can transport lots of organisms that way, thousands of miles.
We started the day in Hubbards Bridge, an area with low salinity, to have a look at these invaders.
It is clearly wedge-shaped. It's actually quite beautifully golden, particularly in this dark black oozy mud at the bottom of the drain. It's it's like panning for gold a little bit when we go searching for them. They get quite big. They're about 5 or 6 centimetres long, some of the biggest ones, and quite a hefty weight to them.
What do they feed off and what are they surviving on out here?
Well, these are bivalve molluscs, and what bivalve molluscs do is that they filter huge volumes of water. By doing that, they can trap small suspended particles of algae out of the water, which is what they feed on. So potentially the invaders here, the Gulf wedge clams, could be removing food which otherwise could be available for the native species. And actually we know with other invasive bivalves that they can increase the rate at which the rivers clog up with sediments because they're stopping the process of the silt out to sea.
So that could have quite a large effect on, say, flooding and sort of affecting local ecosystems. And is that all just from this one new species coming into this environment?
So we know relatively little about it, and one of the things we're actually starting to look at in the lab is how efficient the Gulf wedge clam is in filtering particles out of the water compared with the native species. And also by estimating the abundance in the drain here, we can work out how important really these new arrivals are in the functioning of the entire ecosystem.
Across the day, David and his team were working along the estuary, checking the number of Gulf wedge clams at different salinities. With their nets in hand, Justin Kemp, who's doing a master's in invasive species, explained what they're looking out for.
We're just trying to do as many sweeps and counts as we can, so literally just counting, making sure they're alive, so they're closed and you can feel there's actually a clam inside and it's not just an empty shell.
And are these going to be going back to the lab with you, or are you going to just do your measurements and then throw them back into the
These ones will be coming back to the lab with us, to run further experiments on.
And what will those experiments involve?
For me, there'll be feeding rate experiments, so to see how fast these clams are able to filter out food of a known volume of water over about 2 hours. And then we'll be comparing that to native species and see how the feeding rates differ, and that will allow us to sort of make some predictions about the potential impact they're having here.
As the team continued their measurements, it was clear that they were not expecting the Gulf wedge clam to be so abundant.
Sorry, excuse me, I've just sort of pulled out, I don't know, maybe 40 or 50 in one sweep of the nets, and these are all big, sort of golf ball sized things, and I'm quite surprised.
And it seems that the Gulf wedge clam was not the only intruder at the site.
It's a Charophium, so it's a type of crustacean as well. This is rather large, so it's something that I'm quite interested in, just getting back to the lab and just double checking that it's not another species of concern that's just turned up.
When David was out of the water and all dried off, I asked him if there was anything we could do to prevent these invasive species.
We have a technology which we know works against some other invasive bivalves, something called the BioBullet. It's very simple, but it's very effective. What we do is we take product which is toxic to the clams and we encapsulate it in a tasty coating. And you remember I said that these clams can filter large volumes of water. Well, they swallow this poison pill without realising they've taken the poison in, and they die straight away. And what's particularly interesting is that our native bivalves recognise the biobullets as non-food and they spit them out, so they never eat them, so they're totally protected from them. And all the other native organisms that we've tested the biobullets against seem totally unharmed, so it actually offers a potential eradication tool which is really remarkably specific.
David Aldridge from the University of Cambridge, and he's going to be testing the clams that they collected out there in Lincolnshire against their biobullets in the next few weeks. We'll let you know how they get on. Danny, what do you think about this whole question of invasives? Because it's not just confined to a few shellfish around a few estuarine locations. This is big business worldwide, isn't it? It's a serious problem.
Yeah, I mean, my PhD was actually looking at invasive bivalves. I was looking at Chrysostria gigas, which is the Pacific oyster, which comes from Asia. Yeah, I mean, I found that initially their effects were positive. They increased biodiversity because they're providing a structure, a physical structure, that lots of little nooks and crannies that other animals can live in. But once they got to sort of beyond 50% cover, they actually actually ended up decreasing biodiversity, and they also stopped important nutrients from being recycled up out of the sediment into the water column, which could have a knock-on effect to primary productivity. It's really important stuff that he's doing.
Thank you, Danny. From what shouldn't be living on a beach, as we heard there, to what shouldn't be washing up on the beach. Oil spills, sadly, can spell disaster for coastal wildlife. They can poison fish, they pollute the food chain, and they also congeal on birds' feathers, often fatally. Thankfully, scientists at Argonne National Laboratory in Chicago have come up with a helpful solution, and Seth Darling is with us to explain what it is and how it works. Seth, before we get into your solution, can you first tell us how big is the oil pollution problem in the oceans?
Sure, Chris. So we've been spilling oil in water basically as long as we've been using oil. There are documented spills back as early as the early 1900s. Some of the big ones have been the Ixtoc 1 spill in the Gulf of Mexico. That was more than 400,000 tons of oil. And folks remember the 2010 Deepwater Horizon spill also in the Gulf of Mexico. That was actually more than 600,000 tons of oil. And spills continue to happen to this day. In the past year, they've happened in the US, in the UK, and Canada. There are even ongoing spills in places like India, Bangladesh, in the US. But an important point here is that all of these numbers I've just told you are really estimates. There is no good way to know exactly how big these spills are, and also it's not the size that matters necessarily. Sometimes a comparatively small spill like the Exxon Valdez spill in the 1980s off the coast of Alaska can be devastating because they hit a very sensitive habitat.
When that does happen, what's the usual way that we seek to mitigate the effects of the spill? How do we clean it up?
Yeah, so there's lots of strategies that have been developed over the years to try and deal with oil when it gets in water. One of the ways is you can skim it. That's where you basically try and scrape the oil off the surface when you see the slick. A more common technique is we just burn it, which, does help with a little bit with a water pollution problem, but of course it creates an air pollution problem, so that's not an ideal solution. Skimming also is not terribly effective because if there's a lot of action in the sea, waves and so on, you can imagine it's not easy to scrape the oil off the surface. The truth is that most of the oil is never cleaned up at all. We just let Mother Nature take care of it. That's called bioremediation. It's thought of as a strategy for cleaning up. It really is just letting Mother Nature take care of it. And you may remember from big spills, they'll fly planes overhead and dump these chemical dispersants on the oil to break it up into little droplets so that it leaves the surface, goes down into the water column, and that's supposed to help with this bioremediation process.
But of course, none of these solutions are ideal for the very reasons you've highlighted. What's the solution that you've developed at Argonne?
I'll get to that in 1 second. I should also mention that all of those techniques I mentioned are for dealing with oil on the surface of the water. None of them address oil in the water column, where, of course, it wreaks havoc. And you can think back to Deepwater Horizon, these videos of massive plumes of oil under the surface of the water, millions and millions of gallons of oil down there. And there is no strategy available today to address that oil in the water column, and only these sort of iffy strategies for dealing with it on the surface. So what we tried to work on at Argonne is to develop a sponge that would be able to selectively soak oil out of water, both on the surface and inside the water column, and then be able to recover that oil by just squeezing the sponge like you would your kitchen sponge, and reuse that sorbent, that sponge, to go and collect more oil over and over and over again.
When you say sponge, do you literally mean like the kind of thing I would have in my bathtub or wash my car with, or is that a metaphor? Is this something which is sort of similar to a sponge, but it's chemically very different?
I guess both are true. So the material that we start with is a foam, a sponge. Our favorite starting material is polyurethane. I'm sitting on polyurethane foam right now. It's what's used in furniture cushions and home insulation and all kinds of other things. But polyurethane foam or sponges don't have this property of selectively soaking up oil and not water. And so we start with that material, but then we play with the surface chemistry using some technology we've invented at Argonne to give it that property, to impart so-called oleophilicity, loving oil, and hydrophobicity, hating water.
So you add something to the matrix of the sponge so that it actively says, I don't want water molecules, but I do want anything that resembles an oil molecule, and I'll take that into the sponge and soak it up.
Yeah, that's right. It's really just the surface, the interface of all those pores that are inside the sponge. It's just that surface layer that really needs to be modified, because that's the only part that the outside world sees. Inside all the microscopic fibers that make up the sponge, they're still just good old polyurethane.
And how do you deploy this? I've got visions of people leaning over the sides of boats with a sponge and dipping it in the oil. Obviously not practical. How do you do this, and how much oil can you soak up with this?
So there's various strategies you would use based on the nature of the spill and the environment that it's in. For surface cleanup, it could be something like what you described, where you would have pads of this sponge which would be deployed from vessels or towed behind them or so on, and then brought back on board to compress out the oil before being redeployed again. The really interesting challenge that we're pursuing, though, as I mentioned earlier, is cleaning up oil out of the water column itself, submerged clouds of oil droplets. And in this case, our vision is to use fishing trawlers, which are already brought to bear when there is a marine oil spill. They bring in fishing trawlers to tow booms and other things to try and corral oil spills. Our vision is to let them do what they do best, which is trawl. But instead of fishing for fish, you would have nets that were integrated with this sponge, this oleo sponge, to fish for oil.
And in 20 seconds, Seth, could it also do other pollutants? Could you do the same trick and soak up other stuff other than just oil with this?
Absolutely. There's an enormous potential opportunity here. The way in which we manipulate the surface chemistry, there is a huge library of other molecules that we could attach to this sponge to target other pollutants or contaminants that end up in water. You can imagine heavy metals, mercury, lead, and so on, or any of a vast array of other things.
Seth, thank you very much. It sounds amazing. That's Seth Darling. He is from Argonne National Laboratory in Chicago. Now, Danny, have you come across any of the impacts of oiling on marine ecosystems?
Well, actually, yeah, when I was in the Falkland Islands looking for microplastics, I went to the Falklands Conservation. They had a facility set up to help seabirds that had been oiled. Yeah, I got to actually hand feed some recovering penguins, which was actually a very nice experience. You basically get like a little fish, inject it with some warm saline water. You know, it sort of feels like it's alive because it's warm, and then you sort of hold it up and they just come and take it out of your hand. But yeah, unfortunately, a lot of the, as Seth said, it's quite often the smaller oil spills that create more of a problem because it's the frequency, and it's these really small oil spills from small boats can have an effect on individual birds that we're not even aware of exactly how big the impact is.
One of the things that was highlighted about the Gulf of Mexico, the Deepwater Horizons disaster, is that the oil in the water column was hitting tuna, because there are tuna that come to breed in certain areas and it then begins to go into their bodies and you concentrate lots of other toxins and it damages their reproductive fitness because you've got animals that may not have where they were hit with oil but where they want to breed or migrate to gets hit. And so there's a double whammy.
Yeah, and exactly. And what he was saying about the water column, I mean, that's not as visible and not as obvious to the human eye. So there could be huge damage that's been done that we're not even aware of, and especially damage to actual habitats too, where it's, you know, it's washing up on the coast and smothering shorelines and killing sessile animals as well.
So we need that sponge. Danny,
Yeah.
Thanks very much. Now, at this point in the show, it would have been time for Question of the Week normally, but during our Marine Month here on The Naked Scientist, a host of sea critters are going to be taking over instead. So please usher in Critter of the Week. And to get us started, Katie Haler, who isn't a marine critter, has been at home with a hermit crab.
Name: hermit crab. Scientific name: the common hermit crab is also known as Pagarus bernardus. Location: habitats range from the Arctic to South America. Special abilities: upcycling, i.e. finding homely snail shells, and being good in a fight. Mark Briffer from Plymouth University makes the case for this contender for Critter of the Week.
These peculiar creatures have fascinated observers of the natural world for literally thousands of years. Aristotle described them as looking like a cross between a spider and a crayfish.
Drawing from the sci-fi realm, Mark also says that hermit crabs aren't too dissimilar from the facehuggers out of the Alien movies.
The distinguishing feature of hermit crabs is their soft abdomen, which lacks a protective exoskeleton. Instead, they use empty snail shells as portable burrows, with the hermit's head, legs, and claws poking out of the opening. A naked hermit crab looks decidedly lopsided. The long, soft abdomen hangs behind its last pair of legs and usually curls round to one side, ending in a little hardened anchor. The front part is protected by a small carapace, and this is equipped with a pair of stumpy little appendages which brace against the snail shell, 2 pairs of long walking legs, and a pair of claws to the front, with one claw being much bigger than the other. This wonky body helps hermits to fit snugly inside their coiled snail shells. When threatened, they can close off the shell's opening using their larger claw as a trap door.
So apart from good home security measures, what makes the hermit crab such a cool critter?
Hermit crabs put a huge amount of effort into finding, investigating, and even fighting over the empty snail shells that they rely on. And they will just as happily do these things in the lab as in the field. This makes them superb models for scientists interested in how animals gather information, how they make decisions, and especially in how animals fight. In hermit crab fights, an attacker vigorously raps its shell against the shell of a defender, and if successful, the attacker will evict the reluctant defender and get to move into a newly vacated and upgraded home. It's not just about brute force either. Attackers adjust their tactics as the fight goes on, and skillful fighting is also important.
While they do sound formidable, to be named Critter of the Week, surely hermit crabs must have some amiable qualities.
They are true global citizens. They recycle used shells, and in some species, they even form orderly queues for empty shells.
There you have it. Fighting prowess, an eye for a good shell property, and for some, a love of queuing, make the humble hermit crab the Critter of the Week.
And if you would like to nominate a sea critter for us to consider, you can email chris@thenakedscientist.com, find us on Facebook, or tweet @nakedscientist. That wraps things up for this week. Thank you to our guests Danny Green, Matthew Aaron, David Wilcoxon, David Aldridge and Seth Darling. The producer was Izzy Clark. Marine Month carries on next week when we're going to be diving into the shallow seas of reefs and coastal waters to see who lives there and how waves work. The Naked Scientist comes to you from Cambridge University. It's supported by the STFC, the EPSRC and Rolls-Royce. I'm Chris Smith, and from all of us here at The Naked Scientist, goodbye.